Math 110 students, welcome to Chapter 3 on polynomial and rational functions. Now, what do those words mean? Well, that is the question of the hour. Now, remember, we've got a lot of short videos. I used to do fewer, longer videos, but folks would get so bored. I get bored doing them. Y'all get bored watching them. And so now I do them shorter by subject. So it might feel a little overwhelming. I think we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 videos this week in Chapter 3. It's not terrible, okay? Just like 13 videos, 10 to 15 minutes each. So really, we should be having about 6 hours of instruction time a week, and in a 7-week course, 6 hours of instruction and 3 to 5 hours of homework. Well, this will be way less than 6 hours of instruction, but just be sure that you do click through all of the videos that are listed out, note where you are, and then email me the keywords week by week, okay? Now, again, these should be 10 to 15 minute videos, and so that I can't keep it a 10 to 15 minute video, we better get going, right? All right, section 3.1. Today we are talking about polynomial functions. Polynomial functions. These are functions. We want to know, what are they? What do they look like? And how do we identify when one is a polynomial function? Well, these are basically the ones we've been working with most from now. All right, a polynomial function, if you look at this example down here, f of x equals x to the 4th minus 3x cubed. You'll notice a couple things. All of the variables are either to the first power or another whole number power, okay? There are no square roots of variables. There are no variables in the denominator of a fraction, okay? Now, you can have maybe 1/4 x to the 4th. You could have that. But the variable is not in the denominator of the fraction. You can have a fraction in front of the variable, but if you have a variable like x or y underneath the radical symbol, or a variable underneath in the fraction, the denominator of fraction, then it's not polynomial. All of the polynomial functions have the variable to a whole number power. All right. In fact, 16 here has x, but it's to the 0 power, and you don't even have to write that down. Now, you have constants that are the coefficients of the x. The x is the variable. It's the thing that can change problem to problem. But the constants are the numbers in front, the coefficients of each term. So I have a coefficient of 1 for my x to the 4th term, coefficient of -3 for my x to the 3rd term, a coefficient of -8 for my x squared, and so on and so forth. The degree of the polynomial is the degree of the leading coefficient, and so it's the highest exponent on your variable. In this case, our function here, this polynomial function, is 4th degree because 4 is the highest power on the variable. And the domain of all polynomial functions is the set of all real numbers. They don't have any of the problem things for domains. All right, so what are the degrees of these? Well, let's put this first one in order here. So we want the x to the 5th term to come first. Then the 3x term will come in the middle, and the constant -1 will go to the end. So this is a polynomial function of degree 5, okay? Degree 5. However, letter B has the variable underneath the radical sign. It is not a polynomial function. Polynomial function. All right, not. It is not. All right, so far we've had several polynomial functions we've worked with. We don't always call them that. We have a polynomial function like just f of x equals 5 or 0. That's a constant function, okay? That's no degree. wait a second. No, that's not, that's degree 0. No degree is just f of x equals 0. But f of x equal to 5 is no degree or degree 0. Excuse me, not no degree. This one is degree 0, and it's just a constant. Okay. F of x equals 2x plus 1 is degree 1. Highest exponent is 1. And this is a straight line. That's a straight line, a linear function. And then we've done quadratics like f of x equals x squared plus 6x plus 9. That's degree 2, and that forms a parabola, right? Now, all of our rational functions, because we're also going to now add in degree 3, degree 4, degree 5. We've been talking about these early degree ones quite a bit, but now we're going to generalize what we know about polynomial functions. For one thing, all of their graphs are smooth. In other words, there is no gap, there's no corner, there's no hole. You never have to pick up your pencil to draw a polynomial function. Okay. The most basic polynomial function is what we call a power function, where you just have this one term, okay, of degree n. Now, let's think about this one. Let's just do our most basic one, f of x equals x to the n. This is a positive even one. So an x may be f of x equals x squared, or f of x equals x to the 4th. All of these that have an even degree, an even exponent on the highest term, have several things in common. And all of them start and end in the same direction. Remember, like our parabolas, they're going to start and end in the same direction. Domain's going to be all real numbers. Range is going to be not all real numbers, but the range will be a set of wherever it starts going to positive infinity or wherever it starts going down to negative infinity. Let's look at some of these on, let me stop sharing this. Let's go to some of these on our graphing calculator, just so you can see it. So what am I talking about here? Basic functions. Here we'll go to y equals, clear all this guy off, turn off that plot. All right, let's just do x squared. Zoom to our standard window. Okay. All right, starts in one direction, ends in that same direction. How about x to the 4th? So x, and I'll use the caret button to put it to the 4th power. Very similar, starts and ends in the same direction. Let's do another one that's not one of these basic ones. Let's do something like x to the 6th minus 6x squared minus 5. Let's do that one. Notice it starts and ends in the same direction. All of the even ones start and end in the same direction. Now, they don't have to come from up top and end up top. You can if you just put the negative in front. So let's clear this guy off. And now let's do negative x to the 6th plus 3x plus 2. Okay, now if I put a negative in front of the x, you remember what happens there? It's going to flip it upside down. But notice that it still starts and ends in one direction. Okay. Now that's going to be the primary difference between the ones with an even exponent, where they start and end in the same direction, and the odd exponent. Okay. The odd exponents are going to, all right, let me go back here. The odd ones are going to start and end in different directions. We'll zoom in just a little bit. All right, so let's just start with the most basic odd one. Y equals x. This is x to the 1st power. The number 1 is odd, so this is your most basic. You start in one direction and you end in the opposite direction. Okay. How about the next one would be x to the 3rd? Start in one direction, end in the other direction. How about negative x to the 5th? Start in one direction, end in the other direction. All of these with an odd degree, an odd highest exponent. We're going to start in one direction and end in the other. So think about negative x to the 5th, started high, ends low, as opposed to positive x to the 4th minus 3, which is going to start and end in the same direction. Okay. All right, that's the big difference in polynomials of odd degree and polynomials of even degree. All right, let's go back here to our PowerPoint. Trying to keep this 10 to 15 minutes so you don't get bored. All right, so on the left side, we have even degrees, x to the 4th, x to the 2nd. And on the right side, we have odd degrees, x to the 3rd, x to the 5th. All right, so now let's use these to graph these a little bit with some transformations. All right, so think about this guy right here. First of all, let's write it in proper form where the negative x to the 7th comes first. So this is negative x to the 7th plus 2. So this is an odd exponent here. Odd exponent, so we know it's going to start in one direction, end in the other, but it's got that negative, so it's going to be flipped upside down. And then the positive 2 means we're going to pick it up and move it up the x-axis. So let's just go through with transformations. Let's start with just your basic x to the 7th. And like your basic x to the 3rd, x to the 5th, it's going to kind of go down through the origin and up. Now we need to consider the negative. The negative is going to make us flip it upside down across the x-axis. So if you were at negative 1, 1, now you're going to go up here and be at negative 1, positive 1. So this one becomes this point flipped up over the x-axis. This point, 1, 1, now becomes 1, negative 1, flipped across the x-axis. Last but not least, the plus 2 at the end means pick it up and move it up 2 units. And so our final one is picked up, moved up 2 units, and this is negative x to the 7th plus 2 using transformations. You're welcome to stop, slow me down, speed me up, or just rewind. How about 2x plus 1 to the 6th? Couple things. First of all, this one's an even function. Okay, it's going to, and the basic x to the 6th function looks like this. All right, now the 2 is a stretching upward. So when you plug in the x values, we're going to stretch them up by a factor of 2. And so negative 1, 1 becomes negative 1, 2. 1, 1 becomes 1, 2. And then this plus 1 within the parentheses means we're going to move it left 1 unit. Left 1 unit. So we're going to pick it up, move it left 1 unit. So 0, 0 then becomes negative 1, 0. And this is our graph for 2x plus 1 to the 6th. All right, hey. So your key word for this video is degree. Degree. And so that's it for part 1, and then we'll head into part 2 next.